So due to the limited presentation time, I'm going to jump right into it. So kind of all those bullets on the left here is stuff we're all by now familiar with. The reason why we're all here, we understand that PSI poses risks to missions. And if you kind of advance or click once, my focus here is going to be on the fact that we have people now, programs and projects that require some kind of estimation of PSI environments, a definition of the environment or the risk so that they can assess whether to mitigate or accept and make design decisions. Next slide. So in the Propulsion Fluid Dynamics branch at Marshall Space Flight Center, we have a collection of predictive tools that we are using currently to make estimations of PSI environments for the previously mentioned customers. And you have seen already in some of the previous presentations some more detailed descriptions of those tools, how they work, kind of their development status. So my focus here is going to be more on the fact that we have a wide range of tools that have various levels of computational complexity and cost, as well as physical fidelity. And by choosing which tools to apply to which situation, we're able to turn things around in the necessary time frame to make predictions with the best accuracy that we can for the customer's needs. So I'm going to just briefly talk about 6 of our most widely used tools in this tool belt or arsenal of tools that we use. Next slide. So the first of these is our basic continuum Navier-Stokes solver that is kind of our workhorse for doing simulations of rocket exhaust plumes. That's loci chem. And you can see kind of in the center of the chart here an example of a validation study where loci chem was used to simulate various types of plumes, laminar, turbulent, impinging plumes, and then compared to experimental data sets, we have found that we're able to very accurately predict plume structure, shock locations and whatnot, as well as the impingement properties that are relevant to PSI, like the impingement pressure, the shear stress, heat flux, and then integrated loads. So where we do start to deviate a bit from experiment is when we get into highly rarefied regions with higher Knudsen number. Next chart. That brings us to what Rob was talking about earlier, the Boltzmann solver. So we use the loci chem Boltzmann tool. It's the mixed continuum rarefied solver that uses loci chem in regions where the continuum assumption is valid, and uses the Boltzmann solver in more rarefied regions. You can see in the image on the left, the kind of the red regions, red and oranges, are where the Knudsen number is high and the flow is more rarefied, and then the blue and green regions are where we're in the continuum regime. So if we just use loci chem, we're still able to very accurately predict the impingement pressure, just near the stagnation point, as you can see in the plot in the center. But when it comes to the shear stress, especially further away from the stagnation point, moving outward radially as that radial jet expands and the flow becomes rarefied, loci chem tends to overpredict the shear stress, sometimes significantly. We need to there use Boltzmann to capture the shear stress accurately, and when we do use the Boltzmann solver there, we can get the shear stress within 10% of the experiment. Next slide. Some of these images you've seen previously on Andrew's presentation about how we're supporting lunar site planning. Our DTA tool is one that we use most often. That is a post-processing step that takes as inputs CFD solutions of the flow field, and then for a marginal additional computational cost allows us to track individual particle trajectories through the flow field using drag models that are valid for a wide range of Mach, Reynolds, and Knudsen numbers. So this enables us to calculate things like impact velocities and kinetic energies, ranges of over which particles can be ejected, accumulation where the particles land, and the real power of this tool is the ability to rapidly look at a wide range of particle sizes, several orders of magnitude of particle size, different particle shapes or densities, as well as locations from which the particles may have originated or been liberated. So this is most applicable or most useful when we're dealing with very dilute regions of the flow where there are individual particles, not necessarily particles interacting with others in dense clouds. Go ahead to the next slide. We also have our DIGM tool. This enables us to take CFD simulations, or if we wanted, experimental results at fixed altitudes, maybe just a handful of fixed altitudes, and then interpolate the results at intermediate altitudes, apply some kind of an erosion model to get then smoothly varying erosion rates over an entire descent trajectory. And if you'll click to play the animation on the lower right, this is just an example of that smoothly varying erosion rate during a descent of a multi-engine vehicle. And then we can integrate those erosion rates to get the cumulative crater that would be caused during the descent. Next slide. We've directly integrated this DIGM approach with LOSI-Chem to enable dynamic landing simulations. On the left is shown a particular erosion model that is applicable to the viscous shear erosion regime. We calibrated that model to Apollo-derived data and then plugged it in, implemented it into LOSI-Chem in a way that allows us to deform the ground, the mesh on the ground in the impingement vicinity to respond by way of that model to the forces induced by the plume flow. And then all that happens while the vehicle can be dynamically moving relative to the ground so that we can get a two-way coupled simulation of a landing vehicle with the crater forming beneath it. Next slide. And then finally, this is the tool that Manuel had talked about, LOSI GGFS, which is an Eulerian solver that enables us to extend our capabilities to include other erosion regimes beyond viscous shear erosion. So things where we'd have bed fluidization, like diffusion-driven flow or diffuse gas erosion. This also works very well when we have the less dilute regions where we have a lot of particle-particle interactions and are dealing with things like ejecta sheets or filaments. It also enables us to capture where we get redeposition of material that's been removed from the crater. So this tool, while it's computationally quite a bit more expensive, we can use it in conjunction with our DIGM tool to perform a few analyses at fixed altitudes and then use DIGM to interpolate and integrate to get crater formation for diffusion-driven flow regime, deep cratering over a descent trajectory. And then if you look in the lower right corner, you can see an example of where we've done some large-scale validation, where we've compared crater depth and ejecta against the PFGT data. Next slide. So just to conclude here and summarize, we are currently using this suite of tools to make predictions of PSI environments for a large list of customers. You can see there on the left, people who need to make design decisions. We're continuously adding to and improving the tools, primarily by doing additional validation with additional data sets as they become available, by combining tools to be able to use them where we have mixed regimes, and then expanding that capability. One of the things that you just heard Raymond had talked about, we have quite a bit of pull from people who are interested in dust and obscuration, and so adding tools like that and those, including those capabilities in our suite, is stuff that we're currently pursuing. So thank you.